It is disheartening to hear about poor electrical work and a lack of oversight by inspectors. Unfortunately, similar situations do occur. Here are some examples: unqualified electricians. Work performed by unlicensed or inexperienced electricians can lead to serious safety hazards. Secondly, lack of inspections. Inspections are essential to ensure that electrical work meets code standards. However, some jurisdictions may have lax inspection practices or inspectors who fail to thoroughly examine the work. Thirdly, political connections. In some cases, contractors may have favoritism or connections with inspectors, leading to biased or lenient inspections. Fourthly, understaffing. A shortage of inspectors can result in rushed or incomplete inspections, potentially missing critical safety deficiencies. Poor electrical work can have severe consequences, including fire hazards. Loose connections, overloaded circuits, and improper grounding can lead to electrical fires. Electrical shocks can occur with exposed wires or faulty equipment, causing dangerous shocks. Property damage can result, as electrical fires can cause significant damage to property and belongings. Severe electrical shocks or fires can result in serious injury or death. If you witness or suspect poor electrical work or inadequate inspections, it is important to report it. You can contact the local electrical authority and report violations to the local electrical code enforcement office. You can also contact the state regulatory agency and report unlicensed or unqualified electricians to the state regulatory agency. You can also share your concerns with the National Fire Protection Association, which advocates for electrical safety. It is also crucial to prioritize your safety and refuse to work on substandard electrical systems. Several factors must be considered to ensure electrical safety and compliance with regulations. These factors encompass proper wiring techniques, adherence to electrical codes, and the importance of thorough inspections. Firstly, wiring methods. Proper wiring methods are essential for safe and reliable electrical installations. This includes using the correct wire gauge for the intended current, ensuring proper insulation, and making secure connections. The National Electrical Code, or NEC, provides detailed requirements for wiring methods, including the types of cables and conductors that can be used in different applications. Secondly, the use of appropriate connectors. Connectors are used to join wires together and to connect wires to electrical devices such as outlets, switches, and circuit breakers. It is crucial to use connectors that are specifically designed for the type of wire being used and for the intended application. For example, when connecting copper wires to aluminum wires, it is necessary to use connectors that are rated for this purpose to prevent corrosion and overheating. The NEC specifies the types of connectors that are permitted for various applications. Thirdly, secure mounting and support. Electrical wires and cables must be securely mounted and supported to prevent them from being damaged or becoming a hazard. This includes using staples, cable ties, or other approved methods to support the wires at regular intervals. The NEC provides detailed requirements for the spacing of supports and the types of materials that can be used. Fourthly, junction boxes. Junction boxes are used to enclose wire splices and connections. They provide a safe and accessible location for making connections and protect the wires from damage. Junction boxes must be properly sized for the number of wires and connections they contain, and they must be securely mounted. The NEC specifies the types of junction boxes that are permitted for different applications. Fifthly, grounding. Grounding is an essential safety measure that helps to protect people from electrical shock. Grounding provides a low-resistance path for fault current to flow back to the source, which causes the circuit breaker or fuse to trip, interrupting the flow of electricity. All electrical systems must be properly grounded, and the grounding system must be inspected regularly to ensure that it is functioning properly. Sixthly, overcurrent protection. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect electrical circuits from overloads and short circuits. These devices interrupt the flow of electricity when the current exceeds a safe level, preventing damage to the wiring and equipment. It is crucial to use the correct size over current protection device for each circuit, and the devices must be properly installed and maintained. Seventhly, adherence to the National Electrical Code, or NEC. The NEC is a comprehensive set of standards that governs the safe installation and maintenance of electrical systems. It is updated every 3 years to reflect changes in technology and industry best practices. All electrical work must comply with the requirements of the NEC, and it is essential for electricians and inspectors to be familiar with the latest edition of the code. Eighthly, permitting. Electrical permits are required for most electrical work to ensure that the work is performed safely and in compliance with the NEC. Permits are typically issued by the local building department, and they require the submission of plans and specifications for the proposed work. Inspections are conducted after the work is completed to verify that it meets the requirements of the NEC. Ninthly, inspections. Electrical inspections are an essential part of ensuring electrical safety. Inspections are conducted by qualified inspectors who are trained to identify potential hazards and code violations. Inspectors examine the wiring, connections, grounding, and other aspects of the electrical system to verify that they meet the requirements of the NEC. If violations are found, the inspector will require them to be corrected before the system is approved for use. 10thly, qualified electricians. Electrical work should only be performed by qualified electricians who have the necessary training and experience. Qualified electricians are familiar with the NEC and other relevant standards, and they have the skills and knowledge to perform electrical work safely and correctly. They are also able to identify potential hazards and take steps to mitigate them. Neglecting these factors can lead to serious consequences, including fire hazards, electrical shocks, property damage, and injury or death. It is crucial to prioritize electrical safety and to ensure that all electrical work is performed in compliance with the NEC and other relevant standards. Here are some additional details regarding the specific issues mentioned. Firstly, the lack of Romex connectors. Romex, or non-metallic sheath cable, is a common type of electrical wiring used in residential buildings. When Romex cable enters a junction box or electrical panel, it must be secured with a connector that is designed to protect the cable from damage and to prevent it from being pulled out of the box. The NEC requires the use of connectors for Romex cable to ensure that the cable is properly supported and that the wires inside the cable are protected from abrasion. Secondly, unstapled wires in the attic. Electrical wires that are run in attics must be properly supported to prevent them from sagging or becoming damaged. The NEC requires that wires be supported at intervals not exceeding 4.5 feet and within 12 inches of each box or fitting. Staples, cable ties, or other approved methods can be used to support the wires. Thirdly, permitting after the work is done. Electrical permits are required for most electrical work to ensure that the work is performed safely and in compliance with the NEC. The permit process typically involves submitting plans and specifications for the proposed work to the local building department and paying a fee. Inspections are conducted after the work is completed to verify that it meets the requirements of the NEC. Obtaining a permit after the work is done is a violation of the NEC and can result in fines or other penalties. Fourthly, inadequate inspections. Electrical inspections are an essential part of ensuring electrical safety. Inspections are conducted by qualified inspectors who are trained to identify potential hazards and code violations. Inspectors examine the wiring, connections, grounding, and other aspects of the electrical system to verify that they meet the requirements of the NEC. Inadequate inspections can result in serious safety hazards being overlooked, which can lead to fire, electrical shock, or other injuries. It is important to report any concerns about inadequate inspections to the local building department or other appropriate authorities. To elaborate further, consider the implications of these violations in terms of the NEC. For Romex connectors, NEC Section 314.17. C specifies that when non-metallic sheath cable enters a box, fitting or enclosure, it must be protected from abrasion and securely fastened. Connectors designed for this purpose must be used to ensure compliance. For unstapled wires, NEC Section 334.30 requires non-metallic sheath cable to be secured by staples, cable ties, straps, or similar fittings designed and installed so as not to damage the cable. Cables must be secured within 12 inches of boxes, cabinets, fittings, and other cable terminations, and must be supported at intervals not exceeding 4.5 feet. Regarding permitting, NEC Section 90.4 states that the authority having jurisdiction, OJ, is responsible for interpreting and enforcing the NEC. This authority typically requires permits for electrical work to ensure compliance with the code. Performing electrical work without a permit can result in fines and mandatory corrections. For inspections, NEC Section 90.4 emphasizes the importance of inspections to verify that electrical installations comply with the NEC. Inspectors are responsible for identifying code violations and ensuring that they are corrected. Inadequate inspections can compromise the safety of the electrical system and increase the risk of fire or electrical shock. Poor workmanship in electrical installations can lead to a variety of problems, ranging from minor inconveniences to serious safety hazards. Some of the most common problems associated with poor workmanship include loose connections, incorrect wiring, damaged insulation, undersized wiring, and improper grounding. Loose connections can cause arcing, which can generate heat and potentially start a fire. Incorrect wiring can result in electrical shock or equipment damage. Damaged insulation can expose live wires, increasing the risk of electrical shock. Undersized wiring can overload circuits and cause overheating, which can also lead to a fire. Improper grounding can prevent electrical faults from being safely cleared, increasing the risk of electrical shock. To prevent these problems, it is essential to use qualified electricians who are familiar with the NEC and other relevant standards. It is also important to conduct thorough inspections of electrical work to identify and correct any deficiencies. Additionally, homeowners and building owners should be aware of the potential hazards associated with poor workmanship and take steps to protect themselves and their property. This includes regularly inspecting electrical outlets and switches for signs of damage, avoiding overloading circuits, and using ground fault circuit interrupters, or GFCIs, in areas where there is a risk of water exposure. Furthermore, reporting suspected code violations to the local building department or other appropriate authorities can help to ensure that electrical work is performed safely and in compliance with the NEC. Now let's delve deeper into specific NEC requirements and practical implications. Regarding wire connections, NEC Section 110.14 B specifies that splices and connections must be made with approved methods and materials. Wire connectors must be listed for the specific application and properly taught to ensure a secure connection. Loose connections can create resistance, leading to heat buildup and potential fires. In practical terms, this means using the correct type of wire connector for the wire size and material, such as twist-on wire connectors, or wire nuts, crimp connectors, or terminal blocks. The connectors must be properly installed using the appropriate tools and techniques. It is also important to torque the connectors to the manufacturer's specifications to ensure a secure connection. Regarding cable support, NEC Section 334.30 requires non-metallic sheath cable to be supported at intervals not exceeding 4.5 feet and within 12 inches of boxes, cabinets, fittings, and other cable terminations. Cables must be secured by staples, cable ties, straps, or similar fittings designed and installed so as not to damage the cable. The purpose of cable support is to prevent the cable from sagging or becoming damaged. Sagging cables can be a tripping hazard and can also put stress on the connections. Damaged cables can expose live wires, increasing the risk of electrical shock. Practically, this means using the appropriate type of cable support for the application. Staples should be driven straight and not too tight to avoid damaging the cable. Cable ties should be snug, but not so tight that they damage the cable. Straps should be properly sized for the cable and securely fastened to the supporting structure. Now let's talk about the importance of ground fault circuit interrupters, or GFCIs. NEC Section 210.8 requires GFCI protection for receptacles in certain locations such as bathrooms, kitchens, and outdoor areas. GFCIs are designed to protect people from electrical shock by detecting ground faults and interrupting the flow of electricity. A ground fault occurs when electricity flows through an unintended path to ground, such as through a person's body. GFCIs can detect ground faults as small as 5 milliamps, and they can trip a circuit in as little as 1/40th of a second, which is fast enough to prevent serious injury or death. Practically, GFCIs should be installed in all locations where they are required by the NEC. GFCIs should be tested monthly to ensure that they are functioning properly. To test a GFCI, press the test button on the device. The GFCI should trip and interrupt the flow of electricity. If the GFCI does not trip, it should be replaced immediately. Grounding electrode conductor or GEC connections are another critical aspect of electrical safety. NEC Section 250.64 C requires the GEC to be connected to the grounding electrode system using approved methods and materials. The GEC provides a path for fault current to flow back to the source, which causes the circuit breaker or fuse to trip, interrupting the flow of electricity. The GEC connection must be secure and corrosion resistant to ensure that it will function properly in the event of a ground fault. In practical terms, the GEC should be connected to the grounding electrode system using listed connectors or exothermic welding. The connection should be made in a location that is accessible for inspection and maintenance. The connection should be protected from corrosion by using a corrosion inhibitor or by encapsulating the connection in a waterproof compound. In the context of electrical installations, several key concepts and components play a crucial role in ensuring safety in compliance with the National Electrical Code, or NEC. These include understanding conductor ampacity, performing proper load calculations, implementing effective overcurrent protection, and adhering to grounding and bonding requirements. Firstly, conductor ampacity refers to the maximum amount of current in amps that a conductor can carry continuously under specific conditions of use without exceeding its temperature rating. The ampacity of a conductor is determined by its size, material, insulation type, and the ambient temperature in which it is installed. NEC Table 310.15 B16 provides ampacity ratings for various types of conductors based on these factors. It is crucial to select conductors with adequate ampacity for the intended load to prevent overheating and potential fire hazards. For example, a 14 American wire gauge or AUG copper conductor with type THHN insulation has an ampacity of 15 amps at an ambient temperature of 30 degrees Celsius. If the conductor is installed in an environment with a higher ambient temperature, its ampacity must be derated accordingly. Secondly, load calculations are essential for determining the total electrical load that a circuit or electrical system will be required to carry. Accurate load calculations are necessary to ensure that the electrical system is properly sized and protected. The NEC provides detailed guidelines for performing load calculations for various types of occupancies and electrical equipment. Load calculations typically involve determining the connected load, which is the sum of the power ratings of all electrical devices connected to the circuit or system. Demand factors, which are multipliers that account for the fact that not all electrical devices will be operating at their maximum power rating simultaneously, are then applied to the connected load to determine the demand load. For example, in a dwelling unit, the general lighting load is calculated at 3 volt amps per square foot. Appliance circuits are calculated at 1500 volt amps each, and the electric range is calculated based on the nameplate rating, with demand factors applied is specified in NEC Table 220.55. Thirdly, overcurrent protection devices, such as circuit breakers and fuses, are designed to protect electrical circuits from overloads and short circuits. These devices interrupt the flow of electricity when the current exceeds a safe level, preventing damage to the wiring and equipment. The NEC requires that overcurrent protection devices be selected and installed in accordance with their listing and labeling. Circuit breakers and fuses are rated in amps, and it is crucial to select the correct size overcurrent protection device for each circuit to ensure that it will provide adequate protection. For example, A 15-amp circuit breaker is typically used to protect a 14 American wire gauge or copper conductor with type THHN insulation, while a 20-amp circuit breaker is typically used to protect a 12 American wire gauge or copper conductor with type THHN insulation. It is also important to consider the interrupting rating of the overcurrent protection device, which is the maximum amount of fault current that the device can safely interrupt. Fourthly, grounding and bonding are essential safety measures that help to protect people from electrical shock. Grounding provides a low resistance path for fault current to flow back to the source, which causes the circuit breaker or fuse to trip, interrupting the flow of electricity. Bonding is the process of connecting all metal parts of an electrical system together to create a common ground potential. The NEC provides detailed requirements for grounding and bonding, including the types of grounding electrodes that can be used, the size of the grounding electrode conductor, and the methods for bonding metal parts. For example, a typical grounding electrode system for a dwelling unit consists of a ground rod driven into the earth, a metal water pipe, or a concrete encased electrode. The grounding electrode conductor connects the grounding electrode system to the service equipment, such as the main service panel. Bonding jumpers are used to bond metal parts such as metal conduit, metal enclosures, and metal equipment together to create a common ground potential. Adhering to these concepts and components is critical for ensuring electrical safety and compliance with the NEC. It is important to consult the NEC and other relevant standards for detailed requirements and guidance on electrical installations. Furthermore, qualified electricians should be employed to perform electrical work, as they have the necessary training and experience to ensure that the work is performed safely and correctly. Here are some additional points to consider regarding the original scenario and potential corrective actions. Firstly, a complete electrical inspection. A comprehensive inspection by a qualified and unbiased electrical inspector is essential. This inspection should cover all aspects of the electrical system, including wiring methods, connections, grounding, overcurrent protection, and compliance with the NEC. The inspector should provide a written report detailing any code violations or safety hazards that are identified. Secondly, correction of code violations. All code violations identified in the inspection report must be corrected by a qualified electrician. This may involve replacing wiring, installing connectors, providing proper support for cables, correcting grounding deficiencies, and ensuring that overcurrent protection devices are properly sized and installed. Thirdly, permitting and re-inspection. Once the code violations have been corrected, a permit should be obtained from the local building department, and a re-inspection should be scheduled. The re-inspection will verify that all code violations have been corrected and that the electrical system is now in compliance with the NEC. Fourthly, documentation. All electrical work performed, including the initial inspection, correction of code violations, permitting, and re-inspection, should be properly documented. This documentation should be kept on file for future reference and should be provided to the homeowner or building owner. Fifthly, reporting unethical behavior. If there is evidence of unethical behavior on the part of the original electrician or the electrical inspector, this should be reported to the appropriate authorities. This may include the local building department, the state licensing board, or other regulatory agencies. Reporting unethical behavior can help to prevent similar situations from occurring in the future and can protect the public from unsafe electrical installations. Regarding specific NEC requirements, NEC Section 110.3 B states that listed or labeled equipment shall be installed and used in accordance with any instructions included in a listing or labeling. This means that all electrical equipment, including wiring, connectors, overcurrent protection devices, and grounding equipment, must be installed and used in accordance with the manufacturer's instructions. NEC Section 110.12 requires that electrical work be performed in a neat and workmanlike manner. This means that wiring must be properly supported, connections must be secure, and the overall installation must be aesthetically pleasing. NEC Section 250 provides detailed requirements for grounding and bonding electrical systems. These requirements are designed to ensure that electrical systems are properly grounded and bonded to prevent electrical shock and to provide a path for fault current to flow back to the source. NEC Section 300 provides general requirements for wiring methods. These requirements cover a wide range of topics, including the types of wiring methods that can be used in different applications, the methods for supporting and protecting wiring, and the requirements for making connections. NEC Section 314 provides requirements for boxes, conduit bodies, and fittings. These requirements cover the types of boxes and fittings that can be used in different applications, the methods for supporting and securing boxes and fittings, and the requirements for making connections inside boxes and fittings. Remember, this information is for general guidance only, and it is essential to consult the NEC and other relevant standards for detailed requirements and guidance on electrical installations. Qualified electricians should be employed to perform electrical work, as they have the necessary training and experience to ensure that the work is performed safely and correctly. Electrical safety is paramount and should never be compromised.